The question. It's okay. Start ಮಾಡ್ಬೋದಾ? Thank you. Power's back. But it looks like the laptop supply didn't go. That's good because my battery is gone. If power goes, if that as long as that is there, it's fine. Yeah. Shall we move on? As I said, each question should not take more than that time. So there's no trick question involved. So. It's just a single number. So if you've taken some time to write stuff, then just put the number that you think matches the answer, and then I'll switch to the next question. Okay, next one. And now, I mean, don't think you have to know all this. I just want to know. I don't want to waste your time by teaching you stuff you already know. So that's why I have all this stuff up. So in case most of you know these things, then we can do more interesting things. So if you don't, then this was all supposed to be part of the course. So yes, you just saw. Sorry, yeah. So there are some functions here and some Fourier transforms. Just match what you think could be. So just write down, whatever, 1C, 2B, whatever you think. They're obviously hand-drawn, so they may not actually be, but can deduce. Does anyone want more time? Do you want one more minute? Okay. Okay, 10 more seconds and I'll change to the next. So again, this is also matching, but it should be slightly easier, I think. I hope. So these are example problems. These are general classes of methods. So just try to see if you can guess for these applications, what class of problems you think will be relevant. Obviously, there may be multiple answers, but I'm hoping there's one most reasonable answer for each. We have one traffic person here, so I hope there's no mistake on this slide. Okay, this one should be quicker, I think. 5 more seconds and I will change. If you want to put a random answer down, it doesn't really help the course, but if you still feel like it, you can do it now. Okay, ready? you have some idea of what needs to be done, you can write just a few words. I'm not expecting long answers. Just say, I think you need to use X, this principle, or you need to use this formula, or anything you think that may be relevant, just write it down. Okay, few more seconds and I'll. Okay, this should be much easier. Actually, I didn't mean to present my introduction first. I was planning to do this first because I wanted an unpolluted view. Now, I already polluted you with things that I have already thought about, right? I wanted to have some general. So forget about anything I said today and just give me maybe 2 or 3 sentences at most on what sampling meant to you before you came to the course today. When you heard the word sampling, for example, what you thought, even if it's a very specific application, that's fine. Or if it's more general, that's fine. Just, it doesn't even have to be sentences, it can be phrases. That's fine. Just to get the idea. Okay, okay, maybe 5 more seconds and then I'll switch to the next one. While writing essays, it's a bit scary. I have to read all of that. Just keep it short, it's fine. Okay, next question. Again, just 3 bullet points or whatever, how many ever you want, but just brief what you expect to learn from this course. At the end of a week, what do you think you want to know? This is probably the most important question. So if you want to take an extra couple of minutes, it's fine. Because otherwise the whole week will be wasted. Okay, you all done? That's it. So if you guys can just pass the sheets down, that'll be useful. And I'll also maintain anonymity in case you're worried. So you can just pass everything down and collect it in front. Oops. Everyone done? Don't worry, nobody will know. Yeah, you can put that anywhere. Don't worry. Okay, again, as I said, don't worry. Some of these things we have meant to cover in the course, right? And the reason I asked some of those questions was because sampling is a very widely used term, and depending on what background you come from, you may mean something totally different. So, if I was teaching this in a university as a course, then hi, come in. Yeah. That's the first slide, believe it or not, of the class today. So, yeah, it's a very general term. And if I was teaching it in the university, I know what courses people have taken. So I have some idea of what their background is. But here, since it's wonderfully diverse, I thought at least I should get some idea of what people want from the course and what it means to them. As you can see, the signal processing people are thinking sampling. Immediately they think of signals, how you have sampled them. It's a huge, so right now there's a big buzz around sampling in the music industry. Somewhat like how it was, as I said, when I was a PhD student in animation. I would say now in rendering, now sampling is a big buzz here in the music industry because a lot of things are going digital. They want to sample sounds made by instruments. It's always been done, but right now we're able to achieve very high quality, and it's again used widely. It's very different from the sampling we're going to talk about. But, in agriculture, people want to know, they want to sample things for diseases, they want to take specimens. And obviously in medicine, biopsies and things like that can be considered samples, but you also have medical samples where you want to test a drug, you give it to 10 people and then you see. So you see, sampling is used very widely. And, there's also, things like today data is not the big issue, right? We have sensors everywhere. We have data pouring in from all sides. And even really advanced computers like, supercomputers that you see, probably everywhere now, including IISc, is insufficient for the amount of data. If you want to process that, many algorithms require computing far superior to what we are able to provide, right? Yet we want everything to be available on consumer devices, right? Nobody has the time and patience and maybe even the money to do this. So here, sampling again is a very important thing because we have lots of data. We need to know if we want a quick estimate of something, we want to know what part of the data is important. And regardless of the field you come from, that may be what you wrote down as sampling. Optimization, obviously there's several applications of optimization and graph theory and so on. So yeah, so sampling is a very wide term. For this course, I'll tell you what sampling is going to be. But in general, the goal is, you observe a few, whatever those few may be. Maybe a few bits, it may be a few blades of grass, it may be a few tissue samples, whatever. You observe a few and you want to estimate trends or statistics for the whole population. Obviously, this is very dangerous, right? There's a very high chance you'll get a bias. So for example, if I want to learn about whether people are happy, right? It's obviously a very bizarre concept. But if I now ask 10 people here, tell me what, are you happy? And 9 people say yes. And I conclude 90% of the planet is happy. It's the obvious error to make. But sometimes in practice, it's not that obvious. We take some samples, observe them. It may seem like these samples are perfectly distributed. For example, I may choose 10 students across the world and ask them, are you happy? Still, I'm biased because I'm choosing only students, right? I may choose people from all walks of life, but I may be biased because I only choose men or only choose women. So it's very hard in practice to do this because we need to consciously be aware of what population we are studying and what we're making estimates about. This is probably the hardest part of sampling. And a lot of the theory came out when people wanted to know about populations and they wanted to do these things like estimate how many people are poor, for example, right? It's a very difficult question, even if it's objectively measurable, below certain income, is a very difficult problem because you can't ask everyone, right? And somehow these things become, and if you only ask the people who are paying taxes, then you're biased. If you only ask, and if you think you're choosing random people, you're biased because you're going to certain locations. So it's a very hard problem to get unbiased. So today in computers, it's very easy. We think we just generate a random number, you get a random number, oh, it's random, it's fine, right? But in practice, it's not that simple. So even if I gave you millions of data, images, pictures, and I ask you to choose a random image, it's quite hard because you don't know what the distribution was to start with, right? So yeah, so this is called the sampling step, and this could be called estimation if you want to estimate how many people are happy. It may be called reconstruction if you're a signal processing person and you want to get the signal back from what you reconstructed. And you may be optimizing and so on. So that's the general goal of sampling. And the key question is, what do you want to observe? So what is this few we want to observe? That is the decision you have to make as someone who decides what to sample, right? So what is it we want to observe? And then what statistics? Do you want to look at the mean? Do you want to look at the maximum, the standard deviation? Right? This is unclear. It depends on your application, and you may have to look at different things. Yeah, so as I said, in these cases, you have no control, right? You don't know what you want to sample, what is the space, and you may not have control over the domain. So if you're doing signal processing and you're recording audio, then your domain is time versus amplitude, right? You may change a few things here and there, but there's not much room for creativity. And ultimately, what you estimate may not be a statistic like a mean or a standard deviation or something like that. It may be reconstructing a signal, for example. And again, as you can see, so if you look at a simple example, right, let's say that smooth curve there is the signal. Let's call it something. It could be anything. It could tell you traffic density. It could be anything. So I haven't said what the y-axis is. And this could be anything as well. It could be time. It could be space. So let's say we have some domain and we have some signal there, and we are only able to make a finite number of observations. So in this case, we have 6 observations. And each of those observations tell you what the signal was there or at that time. Somebody has to decide where these should be, right? In the case of your microphone, your audio signals, it is time, and you have a clock that tells you when to sample. If it is a camera, there's pixels that tell you where to sample, that's fixed. So in those cases, these are fixed. But when you want to design sampling strategies, you want to also ask, where can I put these? Where can I make a measurement? Like in the microphone array I showed, right? And depending on the domain, things vary a lot. Can you read this from the back? Is it big enough? Okay. So you may have a finite or an infinite domain, right? If it's time, for example, you don't know when it ends. If it's space, then you know maybe you're only interested in a finite domain. Yeah, as I said, it could be discrete or continuous. So if you have already taken a photograph and you want to sample something from it, then you know you have a discrete grid of pixels. But if you're sampling the world with the photograph, then the domain is discontinuous, and then you're sampling it, continuous, and you're sampling it with some discrete. points, right? So there are different, and so the types of sampling problems will change depending on what nature the domain has and what strategy, right? So in the case of your cameras or microphones, it is a deterministic strategy. There are pixels placed every regular, sort of at regular spacing. And it doesn't depend on what you imagine if your sensor pixels move around depending on what picture you're taking. Right? And there are such constructions today. And that may be actually quite clever. If I'm taking a picture of a white wall, maybe I only need one pixel. So that pixel goes to the middle and says, I'll sample it and I'm done. Obviously, for consumer cameras, we may not need that. But for specialized equipment, that may be something useful, not because we can't store the data, because often a lot of limitations are on power or maybe transmission bandwidth. So you may not want to transmit if you have a white wall. We don't care about transmitting, right? And you can think of MPEG compression and all these things. Yeah, sure. But they all consume power. So if I took a 50 megapixel, so one of the cameras I have at home is like 45 megapixels, right? If I take a 45 megapixel image of a white wall, first of all, I store all the data, and then I run MPEG compression, and then I do the transmission, the complete waste. So perhaps you can do some adaptive strategy, which tells you, given this is the signal, and this may be true if you're in traffic or in sound or whatever it is, you may have some strategy that you can design to accommodate your constraints. So you can have a predetermined strategy, or you can have adaptive. Now, this doesn't tell you anything about whether it's deterministic or stochastic. By stochastic, I mean you have some random algorithm which picks samples. By deterministic, I mean you've already decided what strategy to use. And you could do combinations of all of these things, right? So if you look at the sampling literature, you will see combinations of these. And they may not explicitly tell you this is this. So one of the hard things about a topic like sampling is you will see it pretty much in every field, but they may not sort of identify the taxonomy, right? They may not tell you we are on a finite domain with this. You may have to read the paper or whatever application and realize that, oh, the domain is discrete. They're using this and they're using that. And that may be actually portable to your application. So that's what I'm hoping this course, from my perspective, helps you do, is if you see a paper that looks like it's completely outside your domain, but has an interesting sampling bit to it, can you identify that as being useful to your domain? That itself is not an easy problem. So I'm hoping that by the end of the course, at least you can do this, right? So the problem, obviously, as you must have guessed, is if you use a finite number of observations, there is going to be error, right? It's almost hopeless to, in some cases, but in some cases it may be somewhat useful. So the question is then, how do you measure error, right? Then once you're able to measure error, questions like, oh, is this sampling method better than this sampling? But then that's with respect to that error metric. So you can say, oh, this error metric may not be relevant to me, so maybe that whole finding is not relevant, right? And of course, it depends on your application and so on. Once you have all that, then maybe you can say, oh, for this application, given this error metric, I need 100 samples or 1,000 samples or whatever it is, right? So it will be interesting if you can build theoretical connections, and that's very, very difficult. So I will show you one example, at least one example through this course of developing this from scratch, from first principles. And you'll see how much work it takes to get some idea of what error is. And at the end, that may be a worst case bound or something. So when you actually go and get your data, it may not tell you much. So that's one of the problems we have to live with. And sometimes, depending on how many samples you use, so let's say I have sampling strategy A and B. Two people are telling me two different ways to sample something. I have some error metric, so I can tell who's better than who. And I think I can say, oh, B is better than A. But the problem is suddenly now if I say, oh, so my institution decides to buy a better processor, they tell me, oh, instead of using 100 samples, now you can use 500 samples. It's not a big change, right? So I throw 500 samples, suddenly A will be better, because maybe B was sort of overfit to deal with fewer samples, right? So it's not just sufficient to know whether sampling A is better than B. We also need to have some idea of trends. If you increase the number of samples, if you increase the nature of the data, all of these are the things that makes analysis complicated. So as you will see in industry, what people do is they don't have time for this, right? And that was another motivation of this course, is if you come from one of these companies that need to use these things, perhaps you don't have time to think about all this, because you need to come out with your product, it needs to roll out. Then you're just picking up sampling strategies out there. A, you need to know what you can pick up. B, you may not have something off the shelf. You may need to design something. Designing sampling strategies is very easy. Actually, you don't need to attend any course to design sampling strategy. Intuitively, we will say, oh, let's just fix a finite grid, right? That's the first thing anybody will do. Anyone who has studied computer science will say, oh, put a regular grid, let me, like a microphone, sample every 5 seconds, so on. And if somebody says that's not enough, I'll sample every 5 milliseconds, right? The problem is not designing the strategy. The problem is usually analyzing the strategy, is to know when will this strategy fail, or when is it excessive, and things like that. When is the error so high that is unusable? And in practice, it may never be. You may end up coming up with a simple strategy, and it may work for you all the time until you hit a constraint like bandwidth or storage or something like that. Or if you're using machine learning, right? So if you're using machine learning, then obviously you have lots of data and you need to choose some subset of the data to do things with, then sampling becomes very relevant. Any questions so far? Please ask questions. I don't mean to put you to sleep, okay? Yeah, so as you can see, there's so many different combinations, and now you throw the error metric, and then I can throw in the number of samples, and I can then add stuff about the nature of data. And if you look at it, the combinations in which you can achieve things are very many. So actually publishing a paper on one of these is not at all difficult, which is unfortunate because there are millions of papers, right? And there are really so many that is very hard to pick out what it is that I will need for my application. So hopefully at the end, this will be a bit easier. I'm not promising any silver bullets, but so hopefully in this, so what I will talk about in this course is reconstruction, signal reconstruction, what I told you earlier. You have some samples, you want to know what that smooth curve is. Numerical integration is something we have not talked about. So instead of just what is the smooth curve, you may want to know what is the area under that curve. Why is that relevant? Because there are many applications which require you to do things like what is the expected time. So that question in the sort of assessment, which was what is the expected value of a function, is an important concept, because whether it is traffic or whatever else, you may ask what is the expected number of vehicles passing a junction at a time t, right? Then you need to integrate over some domain. So we will see what that is. So that's something this course will cover. And I will show you using a couple of applications that I'm comfortable with. I've shown you applications that I do research in, but I think for the purpose of teaching, I'm happy to talk about that outside, but for the purpose of teaching, I think these two will be most illustrative because they're more mature. In some sense, people have been doing them for a while. Okay, so that's what I hope this course will cover. Do you have any questions? Yes, that is the key. The key is the whole analysis will change, but also error changes. The way, whether you want to do reconstruction, integration, or optimization, the same sampling strategy may perform very differently. So something that is what was believed. That is what was believed. Actually, yeah, that's a good question, because for people who have studied any signal processing, right, you know of Nyquist theorem, sampling theorem, you have to sample it twice, and all this stuff, right? And there were many results, and people believed that was hard. A lot of people worked on it because they thought it was hard, and it was hard. And it was also relevant because people were collecting time series and wanting to reconstruct. But it turns out that the integration problem is actually very hard as well. And people assumed you could get away with without doing much. And yes, so actually we had a paper in which we showed what the connection is. For the same strategy, if you did reconstruction and integration, what would the error be? And we'll be covering that as well. And it turns out you can get away with half the number of samples for the same error, right? For integration, and you can prove it's a nice number like half. So if you have learned per dimension, so if you have d dimensions, then it's 1 over 2 to the d, right? Power d. And if you have learned the sampling theorem, you know you can't sample at twice the frequency, max frequency, or whatever. Here is just the max frequency, which is a very nice result. And for us, it was, when we came up with it, it looked a bit trivial. But then nobody had ever shown this to be the case. And it was really nice because it was clean. It was just half the number of samples. And then we saw that there are many other differences, some of which make integration harder, some of which make reconstruction harder. And for particular applications, it's even more significant. So for anything we want to see visually, there are a lot of other things, because the error metric is not something you can quantify. It becomes, does it look good? Like for computer graphics, it's a very important question. Does it look good? And people still don't know how to quantify these things. Yeah, so the classes of problems are very different. Let's hope the next slide will. So this is over. Does anyone have any questions? Yeah. Yeah. Yes. Yeah, so there are several different views on that. So for example, let's say you have to find, so optimization is, let's say you want to find the minimum. Actually, perhaps that slide which I skipped is coming back to haunt me. So in my overview, there was that last slide. I think that would have, I didn't want to throw that up then because I wanted people to tell me what they thought it was. I thought if I throw that slide up, then, so this slide probably is more illustrative, right? So you have some function and you've observed these orange things. As you can see here, the observations may not lie on the function. There's noise. So when your pixel measures a value of light, it may measure a bit around the actual amount of light coming, right? It may be due to the CCD elements inside. It may be due to various things. And so all of these things, all of these clouds have signals and some observations. The main difference is what we want to do, right? So here, we want to choose a point and ask what is the value there. Okay? And this is known as reconstruction. It may be known as regression by the statisticians. There are several names for it. This is the integration problem. Again, we have studied this from school. We have some curve, and we want to know the area under this. These two are clear, right? So the optimization problem usually is asking where is the minimum. Right? So you want to know where along this direction is the function attaining a minimum value. That is a general view of optimization. Now, you may have control over this. So you may be allowed to query this at different points and use that to find the minimum. But as you can see, if you have multiple kind of oscillations and modes, then it's not easy to guess where the minimum is. So there's no reason, first of all, that you should have a measurement at the minimum, right? I just drew that here to illustrate, but your minimum could have been this one. And you didn't, you maybe you missed an error. And this is very relevant today because a lot of software, a lot of applications today need to optimize at some level. Right? And we have packages that will do this. The thing we have to realize is these packages use some way to sample and decide where this minimum is. And depending on how they sample, they may be highly inefficient or very, very useful. And depending on your data, so if I know that my data has only one minimum, then suddenly this problem becomes very easy. Right? I don't need to do anything. I make 2 measurements, maybe 3 measurements, and I know. If I know that my data doesn't have these kind of bumps that are too squeezed, like I may not have a spike, I will only have smooth movements, then I can develop my sampling algorithm appropriately. But in general, this is a very hard question. So the way most advanced, so again, the reason these things have become very hard now is people have worked on this for a very long time, but they've been doing things in 1D. like this. Now, if you take an image or you take things and you look at the space where people are optimizing, it's up to 1 million parameters. So if you look at what Google does, right, the dimensionality of their space is vast. And now in that space, if you want to look at where is the minimum, the problem becomes really complicated. So you can't stick to simple strategies anymore without paying the price. If you stick to a strategy of I will just comb through this regularly and I take n samples, right? If you have d dimensions, then you have n to the power d. And if d is 1 million, there's probably more atoms than the universe, right? So you're reaching scales where this is not viable. And I think when people started doing signal processing, things were 1D. When sort of the CT imaging and all these things came, it was 2D. Now it became 3D. Now you have time, so you have 4D. So up to 4D, people are sort of stuck to many of these traditional methods for optimization, right? Even in medical imaging, when they have to do optimization, they may take a slice and optimize over the slice, then take another slice, because that cuts your dimensionality. So a very interesting questions that you can straight away think of, right? If instead of 1D, you had 2D, can you take several 1D parts, optimize over them, and then try to guess what? As you can imagine, it'd be very hard to prove that the minimum you get like that is actually a minimum, right? If it's a minimum, maybe it's a bit easier, but if it's some other statistic, it becomes suddenly difficult. And obviously, when you take 1D slices, you lose correlations. So you may have other issues. So these three classes of problems generally require very different analyses. So you could come up with different techniques in each of these, but then if you want to show anything about it being useful, then it becomes hard. Does that answer your question? Sorry, one answered your question? Okay, good. This one, yeah. So imagine in the simplest case, right? Imagine you had a flat function here. Okay, and I have a finite domain. So my domain may be 0 to 1. And I ask you, how many samples do you need? Can you guess? How many samples will I need to estimate the area? Why do you need the 2? What does the first sample do? You don't know. So you don't know. You just need to know. So yeah. So you know the start and end because you know where the domain is, right? So let me illustrate. Right? So you have a fixed domain 0, 1, right? I'm telling you there's a flat function. And I'm also telling you it's between 0 and 1. I don't tell you what this value is, right? And I'm asking you what is the area here, right? So how many samples do you need to guess this area? So you said 2 samples, right? So let's say we stick with your approach. We take a random, do you mean random or 2 position samples? Position, okay, where do you want to position them? Start and end. Start and end, okay. So you get this and you get this, right? So what is the only piece of information that I gave you before this? The only piece of information I gave you is that the function is flat, right? I've told you that the function is flat. Actually, you don't even need the second one, right? You can take a sample anywhere in the domain, anywhere here, and then ask what is the value, you get V. If you have noise, you get V plus minus 1. But if you didn't have noise, you only need 1 sample to do that, right? Now, if I tell you the function is something else, say a parabola, then you can, obviously using your knowledge of mathematics, you can recognize how many samples like you did now. Say maybe now I need 2 or so on. So somehow here the data plays a part, right? Or the prior, like the idea that we know some information, right? So this in machine learning language is called some prior information. So if you see in machine learning, people talk about prior, it's nothing but this. They're giving you some idea of what you think the function will do. So here the prior is parabola, right? So you're assuming that your data will lie in this shape, on this shape, right? There is no reason. So your actual data may do something around it. But if it generally follows that trend, then you'll be able to design a strategy. So if you know it's a prior, if you didn't know any of this, how many samples do you need? So if I didn't tell you anything, I didn't give you any prior, and I tell you this function, right? So I tell you there's no prior, and I give you the same domain, 0 to 1, and I tell you this function can do anything here, and I ask you for this area. What would you do then? Huh? I tell you, you can choose how many ever samples you want. You can choose any number n of samples, right? Where to place them, I'm asking you now. So what would you do as the first step? Where would you place them? So what is the first strategy you would try? You want to fix the points. Okay, so the simplest would be you take your points and you put them at uniform spacing, fix them, right? And then you see what the values of the samples are. Okay, so you have xi is the so this each of these samples is xi, right? Fixed at regular intervals. And this is some function f, we don't know. So this is f of x. And what you have observed is f of xi, right? That's your measurements. For example, how much sound intensity or light for a camera and so on. Okay, so now you have xi. So, and you have f of xi. Now, how do I know what this integral is? So let me call that I. Let's say I equals 0 to 1 integral. Okay, that's what we want to find. That's our goal. Right? So how would you use xi and f of xi to get that? Adding the areas. Okay, so you will take xi is here, xi plus 1 is here, right? Xi minus 1 is here. So what area are you going to add? So you're saying, what you're saying is, let's do this and take the areas of these. What are these shapes? Rectangles. Yeah, if you were born a few hundred years ago, you could have got a named formula after yourself. Right? That's a very famous strategy to add to compute the area, right? And if you were born many years ago, that would have been called whatever your name. Sorry, what's your name? Yeah, so Sangram. So it would be called Sangram's formula. Unfortunately, you were born too late for that. And people have improved it as well, right? So what people did later was they said, look, this obviously what happens is if this is the curve, there's a lot of error here, right? So what they said was, okay, instead of doing that, I'm going to take a trapezoid. So I assume that the function varies linearly. And I'm sure all of you have studied this in your high school. It may be coming back to you now, right? Is they will tell you some trapezoidal rule. And they call it Simpson's rule, right? So depending on how you come up with these approaches. So obviously this is a zeroth order approximation of the function here. You can have a first order approximation, then you have your trapezoidal rule. You can have a second order approximation and so on. And that's a very good strategy, and people have used that for centuries now, right? And these are general class of methods. Good. So that means I don't have to teach you that anymore, since you came up with it. Right? And what is the general name? What is the general name for this class? Newton codes or something. I don't remember. I think it's called Newton codes approach. So the thing is, as you can see, there's a general idea, which is to place these regularly. And then there's a specific idea of, do I want zeroth order, first order? And depending on the formula that people use, it was a different person who came up with it. And so there's a whole class of these. And once you do this, you can also approximate what the error would be, right? Good. Save this. Okay, so that's also yeah. Sorry. Previous page. Sorry, 1 second. Do you need the figure? Yeah. Sorry. Yeah. So good question. Now, the obvious question is, can we not vary the interval? So if you have to vary the interval, what would you do? So now let's say you want to come up with your own named strategy, right? So let's take an attempt 2, because our attempt 1 was foiled by people many years ago. So let's take attempt 2, right? Okay, so now what's your strategy? Now you still have some function here. How will you place your points? They're not regular anymore. Random points, okay. So let's take random points. So now we are saying xi is drawn randomly, right? When I draw randomly, does it mean that it has an equal chance of being anywhere here, randomly everywhere? Or do you want more random points in the middle and less somewhere else? Let's just make it equal for now. Okay, so let's say we draw randomly in 0, 1, right? This was one of the assessment questions, right? So this is the x domain. And we have drawn xi randomly in 0, 1. So our points could lie now anywhere. Okay, now what do you want to do with these samples? So now we have these and we have f of xi again. Right? Again, we have observed these randomly. We have the values at each of these points. So we have this value, this value, this value. So we know these. Let's assume for now there's no noise and we know exactly what the function is. Okay, so now how do you want to estimate the integral? It's a bit more tricky, right? Now if I have this sample and this sample, now doing this rectangle here is a bit tricky, right? This thing kind of goes under and so on. So what do you want to do? What's the most straightforward thing to do? These 2 points, add them and divide them by 2. Oh, you want to add fixed points. Okay, so you want to add fixed points here. Here. You want to add fixed points there. And then use the fixed point formula we did before. But that will not give you an advantage, right? If you're going to do this, why not just do this in the whole domain? Right? But the starting idea was good, right? You want to throw random values. Does anyone know how or want to say how you can do this? Well, it turns out the simplest way to do this is simply average your values. Right? You take 10 values and you get some thing. You just divide by the total number. And this is a very powerful concept. You might have heard what it's called, right? So what you just came up with is called Monte Carlo. So in case you've been scared by this name before, now you know it's very easy. Right? It's a very, very simple process of throwing random samples here and then averaging the values. And it turns out, so this, let's call this mu n is the value, that is the average, right? Now this is an estimate, right, of I. It is not exactly the value of I, but it's an estimate of Y. Why is it an estimate? Because there is no reason, if you take n such values and average them, that it should give you I. Right? But it turns out this simple idea is very powerful in terms of being able to analyze it. Right? So we can actually, what we can do now is we can, wrong display. trying to write on my laptop. So what can be shown is that the expected value of mu n is I. And so this is called an estimator. More importantly, it is called an unbiased estimator of I, which means, so what does this mean? So I haven't gone through your notes, but I will go through them at lunch. And if I feel that maybe it's worth spending time explaining expected value, I'll do that as well. But for now, anyway, we don't need to know the details. We're still at the sort of intro level, right? I didn't mean for the intro level, but your questions are good, so I just kind of went into it. So what this says is, for now, without going to the mathematics, it's saying that if you take an infinite number of samples n, and you do this, then mu n will be I. So you can prove that mathematically, not that mu n is an estimate of I, but that mu n is actually I. So you can get exactly the integral, provided you take an infinite number of samples. Obviously, we can't take an infinite number of samples. But that's good to know, because it means that anytime you provide these averages, the longer you take, the more samples you take, the better. Okay, so now can someone try to guess what the main difference is between this, apart from the fact that this was so, see, without me having to teach you anything, what you've already come up with is two different strategies. Both are in the continuous domain, just to recap. One of them uses deterministic sampling, and the other one uses stochastic sampling, right? This random process here is some stochastic sampling. Every instance will have a different samples. So we have one deterministic sampling algorithm, one stochastic sampling algorithm. So now I'm going to refer to them by these names. So I'll just call that here. Okay. So now, can someone tell me what is the main difference between these two? Apart from the fact that we fix the locations, is there any advantage or disadvantage to each? Do you think? Can you guess why you might want to use one over the other? Without knowing anything about which one has better error and all that. If there is a better prior, okay, that's an interesting point. So the question is, if there's a better prior, so if we think we have a better idea of what the function, so in this case, remember, we did this whole thing because we didn't know anything about the function. In practice, that's a good point. We may actually know that our function's like a parabola or something, right? It may not be a simple parabola. You may have some idea of what it is. Okay, so if you have a prior, like if I tell you it's a Gaussian, or if I tell you it's a parabola for now, why would you say one is better there? So which you said the stochastic is better? Why do you think? Yes. So if your prior, but then how do you bake that? So right now our stochastic model is not sophisticated. It's very basic. So regardless of what the data does, our samples are still going to be random. So what you're saying is, sorry, what's your name? Sunil. So what Sunil is saying is, if we know something like the function oscillates a lot, maybe we can tune this to take that into account, right? Why can't we tune the other method? For example, if we know it's a parabola, and instead of a linearly varying assumption, if we assume a second order, that is a quadratic, then you'll get zero error. Actually, you will get zero error for any n. You don't even need infinite samples. Any n greater than 3, if you take 3 points and you fit the squared thing, you should get zero error, right? Is everyone with me? If you know that's a quadratic, that function, you only need, just like we needed one sample for the flat one, here you take finite n, some very low number, 2, 3, whatever, and you fit quadratics everywhere, then you'll get perfect areas. So in that case, this actually gives you zero error. The other one, you need infinite samples to get zero error, right? Do you still stick with stochastic, or do you think this is better? It depends on the prior, right? So as Sunil said, if your function is varying a lot and you cannot come up with a simple approximation, if it is not piecewise polynomial, so if you fit piecewise polynomials and its piecewise polynomial fits well, then it's fine. So are we? Oh, is there a coffee break in the middle? What time is that? 11? Oh, okay. Okay, sorry, I completely lost track. It's good to have people to remind. Okay, anyway, I'll end with this short idea. Yes, if you have, piecewise polynomials, maybe this can be tuned very well. Okay, so that's a good observation. So, why is number 1 better than number 2, or otherwise, other way around, right? Either way, it could be. In this case, we said 2 is better for complex priors. No, complex is the bad word. Complicated priors. 1 is perfect in a mathematical sense for piecewise polynomials. Okay, so before we end, I'd like to ask, is there anything else you can think of besides priors? Is there any other reason why one may be better than the other, or we can make these decisions? Number of dimensions, okay. So what can happen in the number of dimensions? So as you increase the number of dimensions, what happens? Why is one better than the other? The number of samples will become too many in which one? In number 1. So how many samples do you need here? If you have n samples in 1D, as I said before, you require, we'll come to that. I'll just really leave this session at number of dimensions. Very good. So we can take a break, but it's good to know, because what we have done now is we've recapitulated about 200 years, maybe 250 years of developments in numerical analysis for numerical integration, right? So all these are algorithms people came up with, like what we have done here. When they were faced with the problem, they came up with these solutions, but they were not happy with the answer that I just gave you. They wanted to know what is the exact error. How do you analyze these things? So they're not famous because they came up with the strategy. They're famous because they proved that if you use this strategy, you have certain benefits. Again, I'm coming back to this because it's a very important point. All of us can come up with strategies, and perhaps some of us can even prove them, right? And that proof bit is very valuable. Okay, good. So let's break for a coffee break. 10 minutes? Okay, we'll be back 11:33-ish. So is that can I switch it off here? Or just give it to you? I'll leave it here.